Hey Charles, how you doing?
I'm doing just fine, Michael. How are you doing?
I'm doing pretty well, thanks. I'm happy to get a chance to tell you about something today.
Excellent. And what is it you're going to tell me about?
We're going to talk about regression.
Like progression?
No, regression. So let me tell you about regression. So we are in this section of the class talking about supervised learning. And in supervised learning, we're going to take examples of inputs and outputs. And based on that, we're going to be able to take a new input and predict the corresponding output for that input, right? So this covers all of the things that we're talking about in the context of supervised learning, right?
Right.
Now, what makes regression a special subtopic? We're going to be talking about mapping continuous inputs to outputs, as opposed to what was the other thing that we were mapping? What other kinds of outputs did we think about?
Well, we had discrete outputs and continuous outputs.
Right, and so this is going to be the focus on continuous. So regression seems like sort of an odd word. It doesn't really kind of fit for this. Often I think about regression as, so this is me being all sad and sort of reverting back to a childhood state. And that's, that's in the psychological sense, that's what regression refers to. But it turns out that that's not what it means in this setting. But the story by which those things became linked, I think, is kind of interesting. So let me tell you about that. Okay, so this is a picture of you, Charles.
Okay, I'll accept that.
You can tell it's you because he's really tall, and you're fairly tall, man. I know you don't think of yourself that way, but you think of everyone else as being short, which is really the same thing.
Fair enough.
All right, so let's say that this is Charles. Let's say that this is someone of average height, just someone at random.
hmm
So now let's pretend, Charles, that you have children.
I do have children.
All right, so that's okay, but we can just pretend. Um, and we want to ask the question, what would you expect the average height of your children to be? Would you expect it to be sort of, sort of Charles height or average height or maybe somewhere in between? So let's actually ask this as a quiz. Okay, Charles, so what do you think about this?
Wait, how old are my children?
Let's say what their adult height is going to be.
I would expect them to be a little bit smaller than me.
A little bit smaller than you.
hmm
So their average height of your children, would you say it would be like an average height person, or like your height, or sort of in between?
In between.
In between. All right. So it turns out that if you actually do this, you measure people's heights and you measure the heights of their children, that is in fact what you tend to see. That very, very tall people like you tend to have taller than average children, but the height is between. It actually regresses to the mean. And here we really do mean regresses in the sense of going back to this kind of more primitive state. That if you think about average height people as being like your ancestors, then you as a very tall person tend to have kids that regress back towards that average value, that sort of more older, more ancient value. So does that make some sense to you?
That makes some sense, but one comment and one question. Comment, that is awesome because I've always actually wondered what regresses to the mean actually means. But second, what prevents all of us from being exactly the same height then?
Yeah, so it's what seems to be happening is that there's a kind of a noisy process, and some people turn out to be taller, but then the next generation, there's a little bit of a history effect, and people stay taller, but it tends to drift back towards the mean. So it's sort of like a random walk to some extent.
Ah, that actually kind of makes sense.
All right, so what does this have to do with function approximation or regression? So how does this notion of regression, of falling back toward the mean, have to do with this idea of approximating functions, mapping inputs to outputs? It seems kind of odd. So it turns out that the relationship is, here's the connection between them. So we're going to draw a graph, and on this axis will be the parent height, and on this axis will be the average child height. So if we plot these against each other, here, let me put the mean up here. Let's say that this is mean height for the population. And now say that we sort of imagine that parents of average height will have children of average height, but parents that are really tall, like that hypothetical person from before, will have children that are taller than average but not as tall as themselves. And similarly, people that are very, let's say, of smaller stature, will have children that are also, short, and but not quite as short. Again, closer to the mean. And it turns out that you have this very nice linear relationship between these quantities. And there's an important aspect to this, which is that the slope of this line is less than 1. It's 2/3, right? If the slope of this line was 1, what would that mean, Charles?
That would mean that everybody's children were of the same height as their parents.
Right, right. And so that's exactly right. And so, but if the slope is less than 1, like it turns out to be in real populations, then what's happening is the children are a little shorter than the parents. Children of tall parents are shorter than they are, and the children of short parents are taller than they are. And that's the fact that this is less than 1 is what makes it regression to the mean. Now, this was worked out in, I believe, the late 1800s, and it was just such a beautiful way of connecting all these different quantities together to kind of think of them as being related in this functional way that people said, oh, this is really great. I'm going to use this idea of regression. And what they started to mean, actually, was not this idea of regression to the mean, but this idea of finding a mathematical relationship based on a bunch of measurements of points. So this term ended up getting misused, but that's the term that we have now. So regression now refers to not this idea of collapsing back towards the mean, but the idea of using a functional form to approximate a bunch of data points. Isn't that weird?
That's pretty cool.
There's another example of this sort of idea where a reasonable word, like regression, which was referring to some physical thing in the world due to experiments like psych experiments at this point, became this mathematical concept where the name doesn't really fit anymore. Like there isn't really anything regressing in what we're doing. Mm-hmm. There's another really important example that we're going to get to later in the course. Do you know what I'm thinking of, Charles?
No.
So reinforcement learning is my field of study, and often your field of study.
Often.
And it turns out that reinforcement learning doesn't mean what the words mean anymore, that this was a concept that the psychologists used to explain what they were observing, and then some mathematicians, well, let's call them computer scientists, took the word themselves, started to use it, and used it wrong, but now it's stuck. And regression is another example like that. The word is sort of being used wrong, but it's stuck, and that's what we're going to use.
This explains why every time I have a conversation with a psychologist about reinforcement learning, we talk past each other.
Yes, they get very confused. I tried to tell them up front, that's not really what I mean, but I'm going to use the words anyway, but it still confuses them. All right, so one of the things that's very helpful about regression is that in many ways it's very simple to visualize, it's very simple to think about what some of the issues are, and all the various topics in machine learning that are really important to understand and sometimes are difficult concepts really do come up in a fairly easy to understand way. So what I'd like to do now is to step through an example of doing some regression and to point out what some of the pitfalls are and how they're generally handled in the machine learning context. So this graph that I put up here is, we just made these numbers up, but it's supposed to tell us a little bit about housing prices. So let's imagine that we're off to buy a house, and what we notice is there's lots of different houses on the market, and there are lots of different sizes, right? So the square footage of the house can vary, in this case of the houses that I visited, between about 1,000 to 10,000 square feet. And of course, as you get bigger houses, you tend to get more, the prices tend to go up too, right? So the price that the house cost tends to rise with the size of the house. So what I've done here is I plotted as a little X, say a set of 9 houses that I've observed. Start off over here with a house that's 1,000 square feet and it costs $1,000. I don't know what era this happened in. And we end up with a house that is 10,000 square feet and costs about $6,000. Again, this is not true in Providence, Rhode Island, I'll tell you that.
Are you sure?
Yeah, I'm pretty sure.
Yeah, it's certainly not true in Atlanta, Georgia.
So, all right. So imagine that this is the relationship that we observe, and now we want to answer a question like, well, what happens if we find a house on the market and it's about $5,000? What do you think a fair price for that would be? So, what do you think, Charles? Looking at this, what do you think a fair price for a 5,000 square foot house would be?
Apparently, about $5,000.
About $5,000, right? So, how did you do that?
I looked at the graph. I went over to 5,000 square feet on the x-axis, and I went up until I found where one of the x's was on the y-axis, and I said, oh, that's about 5,000 square feet.
Well, but there was no corresponding point for that. So you had to interpolate or something based on the points that were there. You had to kind of imagine what might be happening at the 5,000 square foot mark, right?
That's true. Although this one was a little easy because at 4,000 and 6,000 square feet, they're almost exactly the same.
And so that's to you made it feel like there was probably that's probably the level where things in this range would be.
Yeah.
Okay. All right. That seems kind of reasonable. So sure. Though what we're going to do in this case is actually try to find a function that fits this.
Mm-hmm.
All right, so what we can do is actually say, well, what if there's a linear relationship? What would be the best linear function that captures the relationship between the size and the cost? So what I have here is, it turns out, of all the possible linear functions, this is the one that minimizes the squared error, the squared deviation between these x points and the corresponding position on the green line. So it finds a way of balancing all those different errors against each other, and that's the best line we've got. Now, in this particular case, it's interesting, right? Because if you put your idea of 5,000 square feet, look what this line predicts. It's something more like $4,000, right? Do you see that?
I do. That doesn't seem right to me.
It doesn't. Yeah, it doesn't really look like a very good fit. But it does at least capture the fact that there's increasing cost with increasing size.
That's true.
All right, so it's worth asking, how do we find this best line? So again, there's an infinite number of lines. How do we find one that fits these points the best? And again, we're defining best fit as the one that has the least squared error, where the error is going to be the sum of the distances between these x points and the green line that we fit. I'm not even sure that this really is the best fit in this case. I just kind of hand drew it. So okay, so is this something that we would want to solve by hill climbing, which is to say we kind of pick the slope and the intercept of the line, and we just kind of try different values of this until it gets better and better, and then we can't get any better and we stop? Can we do this using calculus? Can we use random search? We just like pick a random M, pick a random B, and see if we're happy with it? Or is this the sort of thing where we probably just want to go and ask a physicist because it involves like continuous quantities and we're discrete people? And that's the correct answer. All right, so let's actually go through that exercise and just derive how we do that, because it's not so bad in 2 dimensions, and it generalizes to higher dimensions as well.
Okay.
So it turns out that we can use calculus to do this. I am not going to step through the 2-variable example for reasons that I am embarrassed to say, but I am going to show you a different example. So imagine that what we're trying to do is that we've got a bunch of data points, and we're trying to find the best constant function, right? So the best function that has the form, the value of the function for any given x is always the same constant c. All right, so if our data looks like this, we've got a bunch of x's and a bunch of y's, then what we're going to do is we're going to say for any given value of c, any given constant, we can have an error. What's the error going to be? The error is going to be the sum over all the data points of the squared difference between that constant that we chose and what the actual yi value is. So that's really
Michael?
these differences here. Yes, Charles?
Can I ask you a question?
Sure.
Why are we doing sum of squared errors?
There's many different error functions, and sometimes call a related concept called the loss function. There's lots of different ones that could work. You could do the absolute error, you could do the squared error, you can do various kinds of squashed errors where, you know, the errors count different depending on how much deviation there is. It turns out that this one is particularly well behaved because of this reason that I'm explaining now, that because this error function is smooth as a function of the constant c, we can use calculus to actually find the minimum error value. But there's lots of other things that could work, and they actually do find utility in various different machine learning settings.
Okay.
So just now using the chain rule, if we want to find how does this error function output change as a function of the input c, we can take the derivative of this sum, you know, bring the 2 over times this, times the derivative of the inside, which is -1 in this case. And now this gives us a nice smooth function saying what the change in the error is as a function of c. And if we want to find the minimum, what do we have to do to this quantity?
You set it equal to 0 because that's what I remember from calculus.
That's right. So in particular, if the error, you know, the error function is this nice smooth thing, the derivative is negative and then 0 and then positive. When it hits 0, that's when the thing has bottomed out. All right, so now we just need to solve this equation for c. So we have one equation and one unknown. All right, so that gets us this. But this quantity, it's just the constant added to itself n times, so it's n times c. If we move that to the other side, we get n times c. N is the number of data points, as you recall, is the sum of the yi's. We divide through by n, and what do we see? So what is it, Charles?
The best constant is the average of all your y's.
Right, it's the mean. The mean comes back. Right, so in the case of finding the best constant here, we just have to average the y's together, and that gets us the thing that minimizes the squared error. So squared error is this really nice thing because it tends to bring things like mean back into the picture. It's really very convenient. And it generalizes to higher order functions here, not higher order functions, but more variables like lines. Sorry, lines that have some non-constant slope. By doing the same kind of process, and things actually work out really nicely. All right, so now let's get back to our data set that we were looking at before. So again, the idea is that we're going to try to find a way of predicting the value for various points along the way in this curve. And one thing we could do is find the best line, but we also talked now about finding the best constant. Turns out these all belong to a family of functions that we could fit, which are functions of this form. Right? We've got x is our input, and what we're going to do is we're going to take some constant and add that to some scaled version of x times some scaled version of x squared plus some scaled version of x cubed all the way up to some order k. And we've talked about k equals 0, the constant function, and k equals 1, the line, but there's also k equals 2, a parabola. Would a parabola be a good choice in this particular case?
Yes.
It does seem like it's got sort of, curvy downy nature, right?
Mm-hmm.
But it's going up, but then it's kind of flattening out, and maybe we could imagine that it starts coming down again. At least over the course of these points, it doesn't come down again, but at least it sort of flattens out. So let's take a look at that. Let's take a look at the best parabola to fit this. All right, so here we go. We've got the best line now, the best constant function, which is just the average. We have the best line with some slope to it. That's the green one. We have now the best parabola, and look, it does a nice job, right? Kind of gets tucked in with all those other points. So what do you think? Is this the best way of capturing this particular set of points?
Well, if the only thing we care about is minimizing the sum of squared error, my guess is that the parabola has less squared error.
Yeah, there's more degrees of freedom, and so at the worst, we could have just fit the parabola as a line, right? We can always just set any of these coefficients to 0. So if the best fit to this really was a line, the best fit to this data point was a line, then the parabola that we see here wouldn't have any curve to it. So yeah, our error is going down as we've gone from order 0 to order 1 to order 2. So can you think of any other way of getting the error to go down even more?
How about order 14 million?
Interesting. Well, in this particular case, given the amount of data that we have, we can't go past the number of data points. After that, they're really unconstrained.
Okay, then how about order 9?
Order 9 is a good idea. But just to give you an idea here, we're going to step up a little more. This is order 4, and look at how lovely it can actually capture the flow here. It's a very faded order 6. And in fact, the best that we can do here is, the highest order that works is order 8. And son of a gun, look what it did. It hit every single point dead on in the center. Boom, 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 boom. It used all the degrees of freedom it had to reduce the error to essentially 0.
Excellent.
So one could argue that this is a really good idea. Though if you look at what happens around 9,000, there's some craziness. Do you see that?
I do.
To try to get this particular parabola to hit that particular point, it sent the curve soaring downward then up again.
Well, it also did that between 6,500 and 8,500. It sent it flying
yes,
way
good
up.
point.
Way off the
Right,
screen.
right. That's right. It went off the top of the plot. So, yeah, that's kind of interesting. But let's just to show that we really are, as we have more degrees of freedom, we're fitting the error better. Let me show you what it looks like, the amount of error that we got for the best fit for each of these orders of k. All right, and so what you see when we actually plot the squared error, this function that we're trying to minimize, as we go from order 0 to order 1, order 2, order 3, order 4, to 5, all the way to 8, by 8, there is no error left because it nailed every single point. So, it's kind of good, but it doesn't feel quite right. Like the curves that we're getting there looked a little bit crazy. All right, so let's do a quiz, give you a chance to kind of think about where these trade-offs are actually going to be. So we're going to pick the degree for the housing data, and your choices are going to be the degree 0, 1, 2, 3, or 8. So a constant, that's the first choice. Or a line that has some slope that, sort of increases with the data, that's your second choice. Or it could be we use a degree 2 parabola, so it sort of goes up and then levels off. Or it might be a little hard to see, but here's a cubic that goes up, flattens out a little bit, and then rises up again at the end. Or we could go with the full Monty, the octic. You can see that might not be spelled correctly. That actually has enough degrees of freedom that it can hit each of these points perfectly. Like that.
The Atari line.
Good, you got that in. So, Charles, how would we go about trying to figure this out?
How would we go about trying to figure this out?
Yeah, what do you think? Which one would you choose, and how would you choose it?
That's a good question. Well, just given what you've given me, I'm going to guess, I think smartly guess, that probably k equals 3 is the right one. And
K equals 3.
And I'll tell you why. It's because 0, 1, and 2 seem to make quite a few errors. 3 does a pretty good job, but doesn't overcommit to the data. And that's the problem with 8, is that 8 says, the training data that I have is exactly right, and I should bend and move heaven and earth in order to match the data. And that's probably the wrong thing, certainly if there's any noise or anything else going on in the data.
Right, so it sort of seems like it's overkill, especially that it's doing these crazy things between the points, whereas the cubic one, even though it clings pretty close to the points, it stays between the points, kind of between the points, which seems like a really smart thing. So so that turns out to be the right answer, but let's actually evaluate that more concretely. All right, so we talked through how it works when you've got you're trying to fit your data to a constant function, a zero-order polynomial. But let's at least talk through how you do this in the more general case. This is what I've been doing to fit various curves to the data, at least implicitly. So what we're really trying to do is we've got a set of data, x and y, set of n examples of x's and their corresponding y's. And what we're trying to find is these coefficients, C0, C1, C2, C3. Let's say if we're trying to do cubic regression, where C0 gets added to C1 times x, which gets added to C2 times x squared, which gets added to C3 times x cubed, and we're trying to get that to look a lot like y. Now, we're not going to get it to exactly equal y, but let's pretend for a moment that we could. We have a bunch of these examples, and we want it to work for all of them. So we can arrange all these constraints, all these equations, into matrix form, if you're familiar with linear algebra. So the way that we can write this is, here are the coefficients that we're looking for, the c's, and here are what we're going to multiply them by. We're going to take the x1 and look at the 0th power, the first power, the second power, the third power, and that equation, I'll use my hands because I always need to use my hands when I do matrix multiplication. So you're going to go across here and down there to multiply these and add, and that needs to correspond to y1. And same thing, this now, the second row multiplied by these coefficients need to give us our y2, and so forth. All right. So if we arrange all these x values into a matrix, and we'll call it, x, and then we have these other guys, and we'll call this w, like the coefficients. Obviously, w stands for coefficients. And we want that to sort of equal this vector of y's. And we basically just need to solve this equation for the w's. Now, we can't exactly solve it because it's not going to exactly equal, but we can solve it in a least squares sense. So let me just step through the steps for doing that. All right, so here's how we're going to solve for w. So what we're going to do is pre-multiply by the transpose of x, both sides. I mean, really what we wanted to do at first is if we're solving for y, we need to multiply by the inverse of x. But this isn't really going to necessarily be well behaved. But if we pre-multiply by the x transpose, then this thing is going to have a nice inverse. So now we can pre-multiply by that inverse. All right. Now, conveniently, because this has a nice inverse, and inverses cancel each other, we get that the weights we're looking for can be derived by taking the x matrix times its own transpose, inverting that, multiplying by x transpose, and then multiplying it by the y. And that gives us exactly the coefficients that we need to have done our polynomial regression. And it just so happens that we have some nice properties in terms of these x transpose x. Not only is it invertible, but it does the right thing in terms of minimizing the least squares. It does it as a projection. Now, we're not going to go through the process that by which we argue that this is true.
Does it have something to do with calculus?
It most likely has something to do with calculus. And we'll get back to calculus later. But in this particular case, we're just using projections in linear algebra. And most importantly, the whole process is just we take the data, we arrange it into this matrix with whatever sort of powers that we care about, and then we just compute this quantity and we're good to go.
Okay.
All right, now part of the reason that we can't just solve these kinds of problems by solving a system of linear equations and just being done with it, the reason we have to do least squares is because of the presence of errors. The training data that we are given has errors in it, and it's not that we're actually modeling a function, but the thing that we're seeing is the function plus some error term on each piece of data. So I think it's reasonable to think about, like, where do these errors come from? So I don't know. What do you think, Charles? Why is it that we're trying to fit data that has errors in it? Can't we just have no errors?
I would like to have no errors. Certainly, my code has no errors.
Well,
so let's see, where might errors come from? So they could come from sensor error, right? Just somehow you're getting inputs and you're getting outputs, and that output's being read by some machine or by a camera or by something, and there's just error in the way that you read the data, just an error in the sensors.
All right. Can you think of other ways? I mean, I guess in this case you're imagining that the data came by actually measuring something with the machine. So that makes a lot of sense. What other ways can we put together the data?
I don't know. I could think of a bunch. I mean, the errors could come maliciously. There could be something out there that is trying to give us bad data.
All right, that seems like a possibility. That when the data set was collected, let's say that we're collecting various. This happens a lot. So if you're trying to collect data from other computer science departments and you're trying to put together some kind of collection of, how much do you spend on your graduate students, say, sometimes these departments will actually misrepresent the data and give you things that are wrong because they don't want to tell you the truth because they're afraid of what you're going to do with it.
Yeah, I've noticed everyone does that except for Georgia Tech and Brown University.
Yeah, there are highly honest and reputable universities in my experience.
Yeah, that's what I feel.
Well, another time that you can get data is if somebody's copying stuff down. So what about sort of the idea of a transcription error?
Mm-hmm.
So we're just, we've copied everything, but, there's just some of the lines that got filled in just got mistyped.
Yeah, and you think that's different from sensor error?
Well, it's maybe a slightly different kind of sensor error, right? So sensor errors, we're actually saying there's something physical that's being measured and there's just noise in that. Transcription error is similar, except it's a person, right? There's little blips in the person's head, and it can be a very different kind of error. You can get like transpositions of digits maybe instead of just noise.
Okay. How about one more? How about there's really just noise in the process? So how about that we took an input X, but there's something else going on in the world that we weren't measuring, and so the output might depend on other things besides simply the input that we're looking at. Right. So what would be an example of that?
So an unmodeled influence might be, well, let's look
at the housing data.
Remember,
the housing data.
That's what I was thinking exactly. So in the housing data, we were just trying to relate the size of the houses to the price, but there's a lot of other things like the houses to the price. Location and location, right? Those are three really good reasons that are not in the particular regression that we did that could actually influence the prices. So right, that and the quality of the house and who built it and
even time of day
colors.
Or what the interest rates were that morning versus what people thought they might be the next day. Who knows?
Right, and so all these different things aren't being considered in that particular regression. So we're just kind of imagining that it's noise, that it's just having a bumpy influence on the whole process.
Sure.
All right, so what I'd like you to do is select the ones that you think actually are important, the ones that that could actually come up when you're using machine learning and regression to solve real problems. All right, and if you were paying attention as we were going through this, these are all very common and realistic things. So, these are all true. These are all sources of error. And this is why we really need to be careful when we fit our data. We don't want to fit the error itself. We want to just fit the underlying signal. So let's talk about how we might be able to figure that out. How can we get a handle on what the underlying function really is apart from the errors and the noise that are in it? All right, so let me try to get to this concept of cross-validation. So imagine that we've got our data, which is our training set. We can, again, picture it geometrically in the case of regression. And ultimately, what we're trying to do is find a way of predicting values in the testing set. So what we imagine is we do some kind of regression, and we might want to fit this to a line. And the line is good. It kind of captures what's going on. And then if we apply this to the testing set, maybe that it's going to do a pretty good job. But if we are feeling kind of obsessive compulsive about it, we might say, well, in this particular case, we didn't actually track all the ups and downs of the data. So what could we do in terms of if we fit it with a line and the error is not so great? What else could we switch to, Charles?
We could just use the test set.
No, sorry. What I mean is, if we fit this to a line and we're sort of not happy with the fact that the line isn't fitting all of the points exactly, we might want to use maybe a higher order polynomial.
Oh, I'm sorry. I totally misunderstood
to fit this
you.
better. So if we can fit this with a higher order polynomial, and then maybe it'll hit all these points much better. So we have this kind of other shape, and now it's doing this. It's making weird predictions in certain places. So really what we'd like to do is, what was your suggestion? If we trained on the test set, we would do much better on the test set.
Yes.
But that's definitely cheating.
Why is it cheating?
Why is it cheating? Well, if we exactly fit the test set, that's not a function at all, is it? We exactly fit the test set, then again, that's not going to generalize to how we use it in the real world.
Ah, so the goal is always to generalize. The test set is just a stand-in for what we don't know we're going to see in the future.
Yes, very well said. Thank you.
Actually, that suggests something very important, right? It suggests that nothing we do on our training set, or even if we cheat and use the test set, actually makes sense unless we believe that somehow the training set and the test set represent the future.
Yes, that's a very good point, that we are assuming that this data is representative of how the system is ultimately going to be used. In fact, there's an abbreviation that statisticians like to use, that the data, we really count on the data being independent and identically distributed. Mm-hmm. Which is to say that all the data that we've collected, it's all really coming from the same source. And so there's no sort of weirdness that the training set looks different from the testing set, looks different from the world, but they're all drawn from the same distribution.
So would you call that a fundamental assumption of supervised learning?
I don't know that I'd call it a fundamental assumption of supervised learning per se, but it's a fundamental assumption in a lot of the algorithms that we run, that's for
Fair
sure.
enough.
There's definitely people who have looked at, well, what happens in real data if these assumptions are violated? Are there algorithms that we can apply that still do reasonable things? But the stuff that we're talking about, yes, this is absolutely a fundamental assumption. All right, but here's where I'm trying to get with this stuff. So what we really would like to do is that we'd like to use a model that's complex enough to actually model the structure that's in the data that we're training on, but not so complex that it's matching that so directly that it doesn't really work well in the test set. But unfortunately, we don't really have the test set to play with, because that, again, is going to too much teaching to the test. We need to actually learn the true structure that is going to need to be generalized. So how do we find out? How can we pick a model that is complex enough to model the data while making sure that it hasn't started to kind of diverge in terms of how it's going to be applied to the test set? If we don't have access to the test set, is there something that we can use in the training set that we could have it kind of act like a test set?
Well, we could take some of the training data and pretend it's a test set, and that wouldn't be cheating because it's not really the test set.
Excellent. Indeed, right? So there's nothing magic about the training set all needing to be used to fit the coefficients. It could be that we hold out some of it as a kind of make-pretend test set, a test set, a trial test set, what we're going to say cross-validation set. And it's going to be a stand-in for the actual test data that we can actually make use of that doesn't involve actually using the test data directly, which is ultimately going to be cheating. So this cross-validation set is going to be really helpful in figuring out what to do. So, all right, so here's how we're going to do this concept of cross-validation. We're going to take our training data, and we're going to split it into what are called folds. I'm not actually sure why they're called folds. I don't know if that's a sheep reference.
Why would it be a sheep reference?
I think there's a sheep-related concept that is called a fold. Like, you know, we're going to bring you back into the fold.
Oh.
It's like the group of sheep.
You are just chock full of knowledge.
All right, so what we're going to do is train on the first 3 folds and use the 4th one to see how we did. Train on the second, third, and 4th fold and check on the first one. And we're gonna try all these different combinations, leaving out each fold as a kind of a fake test set, and then average all these errors, the goodness of fit, average them all together to see how well we've done. And the model class, so like the degree of the polynomial in this case, that does the best job, the lowest error, is the one that we're going to go with. All right, so if this is a little bit abstract still, let me ground this back out in the housing example. All right, so here's how we're going to look at this. So as you may recall, in this housing example, if we look at different degrees of polynomials and how well they fit the data, let's look at the training error, the per example training error. So how far off is it for each of the data points? And as we increase the degree of the polynomial from constant to linear to quadratic and all the way up to, well, in this case, order 6, the error is always falling. As you go up, you have more ability to fit the data closer and closer and closer, right? Because each of these models is nested inside the other. We can always go back. If 0 fits best, and I give you 6 degrees of freedom, you can still fit the 0. So that's what happens with the training error. But now let's use this idea of cross-validation to say, what if we split the data up into chunks and have each chunk being predicted by the rest of the data. Train on the rest of the data, predict on the chunk, repeat that for all the different chunks, and average together. So I actually did that. And this is what I got with the cross-validation error. So there's a couple interesting things to note about this plot. So we have this red plot that is constantly falling, and the blue plot, which is the cross-validation error, starts out a little bit higher than the red plot that's got higher error. So why do you think that is, Charles?
Well, that makes sense, right? Because we're actually training to minimize error. We're actually trying to minimize error on the training set. So the parts we aren't looking at, you're more likely to have some error with. So it makes sense that you'd have a little bit more error on the data you haven't seen.
Right. So good. So on this red curve, we're actually predicting all the different data points using all of those same data points. So it is using all the data to predict that data. This blue point, which is really only a little bit higher in this case, is using, in this particular case, I used all but one of the examples to predict the remaining example, but it doesn't have that example when it's doing its fitting. So it's really predicting on a new example that it hasn't seen, and so of course you'd expect it to be a little bit worse. In this particular case, the averages are all pretty much the same, so there's not a big difference. But now let's look what happens as we start to increase the degree. We've got the ability to fit this data better and better and better. And in fact, down at, say 3 and 4, they're actually pretty close in terms of their ability to fit these examples. And then what's really interesting is what happens is now we start to give it more, the ability to fit the data closer and closer. And by the time we get up to order 6 polynomial, even though the error on the training set is really low, the error on this cross-validation error, the error that you're measuring by predicting the examples that you haven't seen, is really high. And this is beautiful. This inverted U is exactly what you tend to see in these kinds of cases, that the error decreases as you have more power, and then it starts to increase as you use too much of that power. Does that make sense to you?
It does make sense. So the problem is that as we give it more and more power, we're able to fit the data, but as it gets more and more and more power, it tends to overfit the training data at the expense of future generalization.
Right, so that's exactly how we refer to this, is this sort of idea that if you don't give yourself enough degrees of freedom, you don't give yourself a model class that's powerful enough, you will underfit the data. You won't be able to model what's actually going on, and there'll be a lot of error. But if you give yourself too much, you can overfit the data. You can actually start to model the error, and it generalizes very poorly to unseen examples. And somewhere in between is kind of the Goldilocks zone, where we're not underfitting and we're not overfitting, we're fitting just right. And that's the point that we really want to find. We want to find the model that fits the data without overfitting and not underfitting.
So what was the answer on the housing example?
Well, so it seems pretty clear in this plot that it's somewhere, it's either 3 or 4. It turns out if you look at the actual numbers, 3 and 4 are really close, but 3 is a little bit lower. So 3 is actually the thing that fits it the best. And in fact, if you look at what 4 does, it fits the data by more or less zeroing out the quartic term, right? It doesn't really use this power.
But that's interesting. So that means it barely uses the extra degree of freedom you give it, but even using it a little bit, it still does worse in generalization.
Just a tiny bit worse. Yep, exactly so.
That's actually kind of cool.
All right, up to this point, I've been talking about regression in the context of a scalar input and continuous output. Scalar input and continuous input. So basically this x variable. But the truth of the matter is we could actually have vector inputs as well. So what might be an example of where we might want to use a vector input?
A couple of things. One, if we look at the housing example, like we said earlier, there are a bunch of features that we weren't keeping track of. So we could have added some of those.
Great, yeah, we could include more input features and therefore combine more things together. But how would we do that? So let's say, for example, that we have 2 input variables that we think might be relevant for figuring out housing cost, the size, which we've been looking at already, but also, let's say, the distance to the nearest zoo. We think that that's a really important thing. People like to live close to the zoo, and so...
But probably not too close to the zoo.
Possibly not too close to the zoo. But let's imagine that it's like size, something that actually... or actually, let's do it the other way. Let's sort of imagine that the further away from the zoo you are, the better it is. Just like the bigger the size is, the better it is.
Mm-hmm.
So how do we combine these 2 variables into one in the context of the kinds of function classes that we've been talking about?
Well, if we think about lines, we could just generalize to planes and hyperplanes.
Right. So in the case of a one-dimensional input, that one-dimensional input gets mapped to the cost. But in the case of 2-dimensional inputs, like size and distance to the zoo, we have something that's more like a plane. We're combining these 2 things together in let's say in a linear fashion to actually predict what the cost is going to be. So so this notion of linear functions generalizes. This notion of polynomial functions generalizes too very, very nicely. All right, there's another kind of input that's important too. That let's think about a slightly different example to help drive the idea home. So let's imagine that we're trying to predict credit score. What are some things that we might want to use as features to do that?
Do you have a job?
I do, actually.
Yes.
Oh, I'm sorry. I misunderstood. So you're asking, so you're saying one feature that could be important for predicting someone's credit score is yes or no, do they currently have a job? Right. Another thing might be...
well, you could ask instead how much money they actually, how many assets they have, how much money do they have? Credit cards.
Great. So things like what is the value of the assets that they own, right? So this is a continuous quantity, like we've been talking about, but something like do you have a job, yes or no, is a discrete quantity. And one of the nice things about these kinds of regression approaches that we've been talking about, like polynomial regression, is that we can actually feed in these discrete variables as well. Certainly if they're Boolean variables, like do you have a job or not, you can just think of that as being a kind of number that's just 0 or 1. No, I don't have a job. Yes, I have a job. What if it's something like, how many houses do you own? That's pretty easy because you could just treat that as a quantity, a scalar type quantity. What about type of job?
Oh, type of job. I like that. How about hair color?
So yeah, how would we do that? If we're trying to feed it into some kind of regression type algorithm, it needs to be a number or a vector of numbers, and they can be discrete. So so how do we encode this as some kind of a numerical value?
Well, we could do something ridiculous, like actually write down the RGB value, which would make it kind of continuous.
Interesting.
That seems insane, but you could do that. Or you could just enumerate them and just assign them values 1 through 6 in this case.
Right, 1 through 6, or they could be vectors like, is it red, yes or no, is it beige, yes or no, is it brown, yes or no, have it be a vector. And actually for different kinds of discrete quantities like this, it can make a difference, right? So in particular, if we just gave them numbers, then it's kind of signaling to the algorithm that blonde is halfway between brown and black, which doesn't really make sense. We could reorder these. Actually, the RGB idea doesn't seem so bad to me.
Except, of course,
Right,
you have an interesting question of what's the real RGB value. It implies that somehow interpolating between them makes sense.
That's right. That's right.
It also implies an order, right? It implies that the scalar order of RGB is somehow means something, that it's no different from saying red is 1 and beige is 2. So if we multiply it, for example, by a positive coefficient, then the more RGB you have, the better or the worse, right?
Interesting. Though, in fact, what I had in mind here is for RGB, it's 3 different hair colors.
I thought the G stood for green.
People don't have green hair; they have gray hair.
But I thought the G in RGB stood for green.
Yeah, it does usually, but I'm making a hair joke.
Oh, I'm sorry. Good. I'm glad you explained that. You know, Michael.
No problem.
I
So
really
yeah.
like the Boolean vector idea.
Yeah, so I imagine that we're going to return to these issues when we start actually encoding problems as machine learning problems.
I think you're right.
But I think that's enough said about regression for the time being.
I agree.
So Charles, what did we learn about regression?
Well, we learned a bunch of interesting historical facts about where the word came from, which I thought was interesting anyway.
Oh, good.
We learned about model selection and overfitting and underfitting and fitting in general. Cross-validation.
We talked about how to do linear and polynomial regression.
Yeah.
That the best constant in terms of squared error is the mean. Use a little calculus for that.
We also did the same thing for, well, we talked about the process for how you would do it in general for any polynomial function.
I think that's everything.
Well, one more thing. And we talked a little bit about representation and how to make that work in regression.
Right. We talked about input representations and what some of the issues are there.
Yeah.
Great. I think that's a good amount.
I think so too.